Hey everyone, I've got a different lesson design or style or method for you today. I think it'll work better for the topic we're doing. So we're going to look through the static versus kinetic friction stuff. The force of friction equals the coefficient of friction times the normal force. I'll review that for you. And then we're going to look at some things about it, about how friction only depends um, on the normal force, and that's kind of weird and hard to believe. And that's why I'm making a video of this so I can help show you the weird situations and explain why they're misleading. So the friction itself, resistance to motion. Question for you is what fundamental force is responsible for friction? Now, I'm asking what fundamental force. People tend to think of force as pushes and pulls and some people might say friction or air resistance or you know things like that. When I'm asking about fundamental forces, there's actually only four fundamental forces in nature. The most familiar you would think of as like electromagnetic forces, like magnetic force, magnetism, and so on. Maybe static electricity from grade 9, repulsions and attractions of charged objects that would fit into this category. The other most familiar would be gravity. Okay, these are listed in strength. So the strongest at the top here. So I'm going to add that on here. Strongest at the top and weakest at the bottom. And those other forces might not be as familiar. You don't have to worry about them for this course, but I'm just sharing knowledge here. Strongest force is called the strong nuclear force. So this is a force that I wish more people would talk about or even think of asking about in chemistry class. When you talk about the structure of an atom, you got the electrons are attracted to the positive protons because opposites attract, right? It's a nice model of the atom. As soon as someone says that, I think everybody should. I wish I had of anyways, and I wish more students would. I'm still waiting. I keep telling my chemistry or my science classes, like I encourage them to ask a question at that point, and the question would be, why the heck don't the protons repel apart, right? Say you had a lithium. Lithium, if you remember from chemistry, has 3 protons and 3 electrons and I don't know, like 3 or 4 neutrons to go along with it, right? So we could do that depending on which isotope of lithium we're talking about. But the neutrons I'll describe in a second why they're there. So anyways, here's the model of a lithium atom. I wasn't totally planning on doing this, but on the fly here, it's making sense for me to do. Oops, double electron there. Anyway, so we've got these electrons that we think of as being attracted to that positive nucleus, right? And so that's because opposites attract, and that everybody's happy with that, and it makes sense. And so these guys are whipping around. We think of them as whipping around in orbit around the nucleus like that, right? And going in circular paths, or if you will, right? So the question, of course, would be if like opposites attract, that makes sense, but why don't the protons repel apart since like charges repel? And the answer is they're held together by an even stronger force. So physicists call it the strong nuclear force because it's such a strong force. It's actually the strongest overall of the 4 types, and it's responsible for holding the nucleus together. In order to have enough strong force to hold against that, quite strong electromagnetic repulsion, there has to be some extra nuclear material of that type in there. So protons and neutrons both carry that strong force, and so some extra neutrons in there help hold it together. And that's why isotopes exist, right? Because this would still be enough to hold it together, and this would be enough to hold it together, and you might even have like an extra neutron to hold it together, and yeah. So all of those different versions are possible for the nucleus. Overall, the chemical behaviors are just based on the electrons, right? So they all behave chemically the same way. Okay, so different isotopes of lithium or hydrogen or whatever are going to, look, taste, smell, react, the same way in chemistry. It's just about electrons. The third one, the last one I'm going to tell you about here, is called the weak nuclear force. And the weak nuclear force is to do with radioactivity. And so it's really to do with the stability of these neutrons. Those neutrons aren't stable on their own. So in this scenario here, this is quite likely not as stable. Certainly if I added one more neutron, it definitely wouldn't be radioactively stable. So it'd be radioactive version, a radioactive version of lithium that physicists could make in a nuclear particle reactor. The reason it wouldn't be stable is because neutrons that aren't paired up with protons just aren't stable. They decay into things, neutrinos and energy and protons and so on. Right. So if you take grade 11 university level physics, there's a section in there we talk about that, beta decay and alpha decay and so on. Anyways, that's a, a little bit of a tangent to start this video, but out of all of those forces, okay, the strong nuclear force that holds the nucleus together, the weak nuclear force to do with radioactivity, gravity that holds masses together, and the electromagnetic force, right? Which one is responsible for friction? Okay, well, it is the electromagnetic, because you've got electrons and protons. Certainly the electrons are in the outer regions of the atoms, and those atoms make up molecules that make up the block of wood and the concrete floor, and and so on. So you get interactions of the positives and negative charges, really probably just the negatives, to be honest, but just for simplicity here, we can talk about how these two positives, for example, would repel. And so if you're trying to push the block to the left, that would try to stop it. Or you could look at all of these positives and negatives all lined up nicely, attracting, kind of like trying to hold the thing in place, right? So it's interactions of those charges that actually makes friction be a thing. A nice simulation, it says next page, so I'll move it here. A nice simulation of this is, second to load up here. This is a little simulation that shows the molecules, or even maybe the atoms of substances, depending on what kind of substance we're talking about. But you take the two substances and you move them together, and so the thermometer here shows the thermal energy, and you should be able to see they're jiggling slightly, and that's the temperature. That jiggling slightly is the thermal energy of the system. We've experienced it as temperature. If you rub these things together, then it's not this simulation doesn't show the pushes and pulls as much, but picture if I slide this thing sideways, it should let me slide it sideways. Pause the video and see why this is. I might have to refresh here. There we go. All right, so slide this thing back and forth, and basically, it's like they're hitting against each other, pushing and pulling on each other, and it makes the vibration increase, right? Vibrational energy increase. So basically, the energy that you're pushing sideways with ends up getting transferred into this jiggling of these molecules. That's why if you rub your hands together, they warm up, right? So that's friction. That's energy being lost or transferred to other forms, right? And so you have in the previous content thing talked about static friction. So if a block if two things are at rest, then that's lots of attractions and repulsions holding things together. And so that's what we've talked about as static friction, which is the larger value. And if the block is moving, you can think of it as attractions and repulsions, making and breaking as it slides. So it's going to average out to less because, you're in between, like you haven't set up an attraction yet and so on, right? And then an even smaller friction value is rolling friction, right? So really, as a tire rolls, the electric fields of the tire get close to electric fields of the road, and so temporarily they start to try to hold on to each other, right, or repel each other, whichever, and so that leads to a small amount of energy transfer as well, but certainly a lot smaller because you're not physically dragging and pushing against the different atoms as things are pushed sideways, sliding, right? So if this in this simulation, it might even actually work. Let me just see if I took this thing and went and touched it and touched it and touched it and touched it and touched it, and that's kind of what a tire is going to do as it rolls, right? You can see that might, that is actually making the temperature go up. So that's but not as much as like sliding back and forth, right? So you picture a surface of a tire coming down, hitting, and then rolling back up, coming down and hitting and rolling back up. That could transfer some energy. That's rolling friction, but a lot less. So this is a little Facebook reel video that I saw recently. I thought I should add this to the lesson, so I'll let this play.
Do you know that at the atomic level we cannot touch anything? Each atom has a nucleus in its center, and around this nucleus there is an invisible field in which electrons move. When two objects' atoms come close to each other, these fields push each other, which gives us the sensation of touch. But in reality, it's not touch, but a repellent force between the two atoms.
So that's along the lines of, you picture how that leads to these interactions, right? These two electric fields are pushing against each other and interacting, right? Now, the next thing is to look at, the friction idea at a fundamental level a little bit more here. I'll show you this guy here, Bozeman Science. This guy's awesome if you want to use him for learning about things, right? Supporting lesson topics in any subject. He's got awesome ones for physics, chemistry, and everything.
So this is a model that makes sense to me. Each of these blue spheres represents an atom, and then these dotted lines represent bonds or chemical bonds between the atoms. But think of them almost like springs that are connecting all these atoms together, and then we have an object. So what happens if I were to just push on it like this? So if I push on that atom right here, it's going to change its shape. And so we're going to start to get tension right here, tension in these bonds here. And so there's going to be a resisting force that's going to be in the opposite direction, like that. What would happen if I were to pull on that atom right here? It's going to stretch it out here. So we're going to have tension all along this way. And so what's going to be the responding force? It'd be in the opposite direction. But let's say we were to push at an angle. If we push at an angle like that, so we're going to go like that. We're now going to have tension right here. Where's going to be the responding force? It's going to be in the opposite direction. And so in all the forces that I'm about to describe, it's the same interatomic cause. There's no difference between a normal force and a tension force. And
so, so the picture, it's not actually even touching there, right? You just have another blue dot repelling that blue dot. So you're pushing on the object, but the blue dots that he's not showing here, its electric field would be repelling the electric field that one, and so on, right? So just to give you a good feel for how this all works and looks and makes sense and so on, right? So this is actually a graph from equipment that I have for measuring force. And so this is the static friction went to a peak value, and then it broke down to an average, fluctuates a little bit, but around 2.5 kinetic friction and around 3 as static friction. There's a little simulation here that you can use if you like. Where is it? Did I not load it up yet? Hang on. If I loaded it up yet. Nope, looks like it didn't. All right, I'll load it up right now. Anyways, a little simulation for friction or friction, whatever. So you get started here, and basically it says, if I remember right how to do this, you start, and it's going to show as you're pulling this thing, friction increase, and then it breaks and it starts to slide. And so you can do this over and over again. It's not super animated or anything, but you can choose different surfaces and so on. Okay. So that's just a little simulation that kind of illustrates like what I would have done in getting a graph like this. Have an object tied to a string, and you, with a force sensor, and you pull harder and harder and harder until it starts to move, and then you move it with constant velocity. Okay. So this video right here, which I'm just going to load it up, actually. I don't want to load that one up yet. Just because it's going to mess up my other video that I have queued up. Let me use this one. Sorry, one sec here. Old school. I'm going to make sure I load it with the right program here so it doesn't mess up my next one. Play with VLC. Wow. I didn't think that ad was going to be in here.
A large box with some heavy masses in it, you can show students that static friction is stronger than kinetic friction. By pulling on the spring scale, you see the force of friction increases and then decreases with kinetic. One more time, you see that static friction will increase to a maximum and then decrease once you start pulling it.
So when you pulled, it spiked up to like 18 or so, and then went down to an average of like 10 or 11 or something. Right, so that is that, and graph from that. All right, so you see or saw I think you saw already the the force of friction, and I think we did it based on the mass instead, but basically you get this straight line all the time, right? So basically if there's more contact force, then there's more friction force, and so the pairs of numbers end up being a nice straight line like this. So intuitively, of course, if there's more contact force between surfaces, there's going to be more friction, right? Experimental results actually would end up being nice like this. They'd be linear, and it would show like a direct relationship, right? And so they're directly proportional. That slope is that constant proportionality, that number that relates the two values. So just like in grade 9 math, we have your y and your x, and then slope is the y equals mx, right? In this case, or if you had a y-intercept of y equals mx plus b. It's basically we know that force, friction divided by normal force is always a constant value. That is that coefficient of friction that you know already from the previous content page, whether it's the larger one, the static, or the smaller one, the kinetic. Okay, so that's where that equation comes from, of course. And so the different numbers you could measure for different substance pairs, like you could model in the simulation. And so the real reason I made this lesson, okay, that was kind of all review-ish, with some added info, of course, but if you're having worked with force of friction equals mu Fn, even just this equation existing, what does that tell you about what the amount of friction depends on, right? So really, it just depends on the types of materials, which is this. So that would be the material types, and of course this thing, which is the contact force, right? That normal force between the surfaces. So it's just that contact force. You can think of this coefficient of friction really as giving you the percentage of the really essentially gravity force or the normal force that opposes or that balances it, right? If an object resting on a surface, anyways, it gives a percentage of the gravity force that's available as friction, right? So if you had a 0.11 coefficient of friction, that means 11% of the gravity force is available as friction for sideways. Right? Noticeably missing from this, which I think a lot of people would think would matter, would be surface area. Right? There's no spot for surface area in the equation. Well, that probably seems weird to people. Like you think you can get more friction by having a larger amount of surface contact, right? One supporting observation of this I like to joke around with is like, generally in life, people with big feet and small feet aren't more or less likely to slip when they have like rubber shoes on concrete. Like it's just not a thing, and there's a good reason for that. Okay, I'll show you experimentally too. Though I have these blocks, and they have one rectangle of felt on one side and two rectangles of felt on the other. And so the red graph is from 2 square units, so this way down, and the green one is from 1 down, sitting on its edge. Okay? And these are the graphs. So see how the force spikes to about 3 and then averages out around 2.5. Spikes around 3, averages out around a 2.5. That particular graph isn't as good. But if you look at this one right here, right, the green and the red are essentially right on top of each other all the way along as you repeat the trial over and over again. Okay, so it's the same force. So surface area is not a factor. That's why that's why the equation is the way it is, and so on, right? Why is it so hard to believe? And I wouldn't blame you if you're at this point going, it doesn't make any sense. What about blah, 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 right? Well, when the blah, blah, blahs come out as what about this situation? It's always going to be about traction that you're comparing it to and having trouble agreeing with the idea, right? So when you look at, traction, I guess I'll go like when you have traction and things are digging in, it's different. So before I get to that, though, I want to show you this really good video here about why it doesn't matter. Okay, so this is friction and the real contact area. I believe it plays with an ad. Yep.
Leonardo da Vinci thought a lot about friction. In his studies, he determined that blocks of the same material and mass experience the same frictional force, regardless of the shape or orientation.
So it's kind of weird, right? Like this one like that, or like this, or like this. Like they all have the same amount of friction. I'm surprised they don't have it on this end for this one, because that's technically the same surface area. So they could have it on the largest surface area, and this could be a medium surface area, and this could be a smaller surface. Long story short, though, doesn't matter, right? How can that be?
The size of the apparent area of contact doesn't affect the friction, which seems counter to what we experience. To understand,
right? So in those situations, the boot in the snow or whatever, and the skate blade and things like that, it seems kind of different, right?
Why? We need to zoom in on the surface texture. At this level, the block is not resting on all of the points of the surface, only a small amount of peak material. When the block is set on a hard surface, the highest peak makes contact and tries to resist the load. Most likely, the load is too great, and the peak crushes or plastically deforms.
So it bends, right? Squishes to have a certain amount of contact area.
More peaks resist the load and crush, further and further until the load is supported. The area of material that supports the load is called the real area of contact. It's typically a very small percentage of the apparent area of contact. For this 12,
so the apparent area of contact would be the full 12 by 12 inches, right? Whereas the real area of contact would be only the peaks of the microscopic texture that would be touching, right?
Inch steel cube, the real area of contact is only about 0.01.
That's crazy. Like for that cube, 12 by 12 should be 12 by 12 is 144, right? So it should be 144 square inches. Instead, it's only 0.01 apparently. That's mind-boggling.
1 inches squared. The amount of friction depends on the real area of contact. And for this case, where the surface deforms plastically, the real area of contact only depends on the material hardness and the force pushing down. The apparent area of contact does not affect the friction at all. However the block is oriented, the amount of peak material making contact remains the same, though it may be distributed differently. Da Vinci observed this fact about friction, but it took modern measurement techniques and microscopes to explain what's real.
So this is like really, they've used modern technology to figure this out, right? For ages, I think to be honest, actually, when I was in high school, it was kind of like, yeah, this is just what we find, and so experimentally we see that this is true, so we do it, we use that information. Now we have the chance of looking at this, electron tunneling, scanning microscope to look at what areas are contacting, and it all makes sense in the end.
Happening. Michigan Metrology provides 3D surface texture measurement.
There you go. Michigan Metrology. So the real area of contact, right? Friction only depends on that, and so it's always there's always just going to be the same amount of squish overall to support the load. Kind of neat, right? So the results for friction are of course undeniable. Like it really works, right? But it's still, for a lot of people, is going to seem like a special case. It's that's only in a physics class. In real life, the size of the tire matters, or the wider the tire, the better, and things like that, right? Or for traction, or whatever the case may be in different scenarios. Or so it's a fairly special case we're talking about here, right? We're talking about just friction, and where there's no surface damage, no digging in, things like that, right? So it's objects sliding while in contact, and the interactions are just the electromagnetic, right? There's no scratching, there's no digging in, and so on. So that electromagnetic force depends on that real area of contact only, obviously, right? So the more common situation is, of course, if there is surface damage, and that is when we start talking about traction. Okay? So traction is much more common in everyday life, which is why the friction reality of Ff just equals mu of n seems harder to believe, right? And so in traction situations, you're digging in, you're grabbing stuff. The surface area does matter, of course, right? There's a imprint left over showing that, and so bigger tires with big knobs grab more ground, get better traction, and so on, right? Another situation you could think of that's makes it hard to believe is, what about these dragsters? Why do they have big wide tires, right? So you look at that and be like, oh, well, why do they have big wide tires? Well, their big wide tires are an advantage because you have to understand that we need these rubber tires to be super soft and sticky and grippy and whatnot, right? And so they need to be pretty soft rubber compounds. Well, that means they can't have really high pressure, right? So if you look at the concept of pressure, this is 100 newtons of force down on just 1 square meter. That's 100 newtons per meter squared of pressure. Whereas this, if you had 4 units of area, that would only be 25, right? So this tire, a tire like this, like a 10-speed, like a road bike tire, they have incredible pressure in those tiny little tires, right? So they have a huge amount of pressure, like 100 plus, psi in them, because that small area needs to hold up the bike and the person. Now, the reason they have those super small tires is because that causes less friction, because there's less interaction of electromagnetic forces, right, with the road, right? So with the dragster, right, they like that, so they can have really low pressure, so they can get the tires really hot and soft and sticky, and then you end up with lots of traction. You get lots of rubber ripping off the surface onto the road and so on, right? You don't need to see a burnout of a motorcycle, I don't think. So you get extra friction because you have that's like super sticky tires, right? So that's it. When you have traction, you're digging in, right? But friction's a very different scenario, and it's just hard to believe as a result. So you'll see this in the content page, and I'm going to put a PDF file of this in there as well, and of course the link for the video that you've already finished watching. All right. So that hopefully that helps. A lot of this is the same as the previous content in terms of like skill set, except for talking a little bit more about why kinetic friction and static friction, why they're different values, and so on. Okay, and this one talks about this first question talks about the idea of traction and friction a little bit there. So I hope that helps. If you have any questions, post questions in the post thing, or email to me, or and all that. And you'll notice this video is playing through my YouTube channel. So if you want to help spread physics information to more students, like and subscribe and stuff, and share it with your friends. Okay, you might have some friends in high school that are in different physics courses. So I have this grade 11 university course all online on my YouTube channel, and the grade 12 course is in progress right now and halfway through. And so if you have any friends in those courses, they might benefit from being able to see in-depth videos like this. So anyways, all good. Thanks for watching, and see you next time.